Hi, welcome to another one of our videos in our chemistry lecture series. We are still on the mole concept, but this time we are looking at calculations involving the mole and molar volumes. Now, the objective that will be covered in this topic will be to perform calculations involving molar volumes. Now, this would be very similar to calculations you saw when we did mass and equations. The only difference is this time we're looking at volumes instead of masses, but the concept is the same. Let us begin. In this section, we are going to state Avogadro's law and look at calculations involving molar volumes at RTP and STP. It must be noted first that Avogadro's law applies only to gases. Now, what is Avogadro's law? Well, Avogadro's law states that equal volumes of gases under the same condition of temperature and pressure contains the same number of particles or molecules. From this statement, it follows that equal volumes of molecules occupy the same volume. So if I have oxygen as one set of molecules and I have carbon dioxide as another set of molecules, and we are under the same condition of temperature and pressure, then if both gases, carbon dioxide and oxygen, are equal, then they would contain the same number of molecules if you count them one by one. That is all the law is saying. So equal volumes of different gases under the same condition of temperature and pressure will contain the same number of molecules. Now note that molar volume of a gas is the volume occupied by 1 mole of a gas, similar to what is the molar mass, the mass of 1 mole of a substance. Same way, the molar volume of a gas is the volume occupied by 1 mole of a gas. Now, anytime the volume of a gas is stated, the conditions of temperature and pressure at which the gas is measured must also be stated. So, look at STP and RTP. We have standard temperature and pressure, which means that the temperature is 0 degrees Celsius and the pressure is 1 atmosphere, or 273 Kelvin and 1.01 times 10 to the 5th Pascal. At RTP, which means room temperature and pressure, the temperature is now 20 degrees Celsius and the pressure is 1 atmosphere, or 293 Kelvin and 1.01 times 10 to the 5th Pascal, which is pressure. If the molar volume of a gas is a volume occupied by 1 mole of a gas, it simply means that 1 mole of a gas at STP would contain 22.4 dm cube. This is just saying that 22.4 dm cube is present in 1 mole. So at STP, the volume occupied by a gas is 22.4 dm cube per mole. So 1 mole of a gas at STP, the volume occupied is 22.4 dm cube per mole. So for every mole, it occupies 22.4. If it is at RTP, which is room temperature and pressure, then every mole of that gas would occupy 24 dm cube. So the volume occupied by the gas at RTP is 24 dm cube per mole. Now, we know that 1000 cm cube is equal to 1 dm cube. And so, when doing mole concept calculations involving volumes, we will get our volumes most times in centimeter cube. Now, this volume must be converted to dm cube. And we do so by simply dividing the cm cube value by 1,000. And that is converted into dm cube. So all calculations involving mole concept, they will be done in dm cube. So remember to convert your centimeter cube into dm cube. Look at the equations here in calculating moles of a gas given volume at STP, or moles of a gas given volume at RTP. Now, number of moles equal volume over 22.4 dm cube per mole if it is at STP, and if it is at RTP, the number of moles is equal to volume over 24 dm cube per mole. Now, let us do some calculations involving molar volume. Now, what is the volume occupied at STP for 2 moles of chlorine, A, and B, 0.5 moles of carbon dioxide? Now, if we're given this problem, the first thing we should do is understand that we are given 2 moles of chlorine. Now remember that chlorine is diatomic. So to do part A, we say that moles is equal to volumes over 22.4. Why 22.4? Because the volume here is at STP, and 1 mole of a gas at STP occupies 22.4 dm cube. So we know that. So we need to calculate the volume. So we must rearrange this equation. So volume is equal to moles times 22.4. And this is what? dm cube per mole. Now it's important to note that the volume is not just dm cube, because if it is dm cube, then we are going to have issues with our units. Remember, it is dm cube per mole. From that, we can see that if I'm working out my volume, then moles would cancel moles. And so the mole here is 2 moles times 22.4 dm cube per mole. So mole will cancel mole. This will give us a value of 44.8 dm cube. So the volume occupied by 2 moles of chlorine is 44.8 dm cube. What about 0.5 moles of carbon dioxide? Again, we're given moles and we want volume. So we would use the moles to find the volume at STP. So for B, volume equal 0.5 times 22.4. Again, remember, your unit here would be moles and your unit here would be dm cube per mole. And so we would now multiply 0.5 moles times 22.4 dm cube per mole. 0.5 is really a half, so we're really halving this value. So we will get 11.2 dm cube. So 11.2 dm cube of carbon dioxide is present in 0.5 moles of carbon dioxide. Now we understand how to calculate volumes from given mole, or mole given the volume at STP or RTP. We are going to apply molar volumes to equations, similar to how we applied mass to equations. Now, this question you've seen before when we calculated the mass of sodium hydroxide that would have been produced from 9.2 grams of sodium. But we also can find the volume of H2 produced at STP or RTP, depending on which one the question asks for. Now in this case, it says, what is the volume of H2 produced at RTP? So right away, we know that we must use 24 dm³ per mole for RTP. From a mass of 9.2 grams of sodium, which reacted with water to produce sodium hydroxide and hydrogen. Same principles that were applied before, we will use now. So we would write our equation plus water, and this will produce sodium hydroxide plus H2. That is your gas, that is aqueous, that's liquid, that's solid. What are we concerned about? We are concerned about the volume of H2 produced from the mass of sodium here. So the first thing we must do is to write our equation and balance it. If we don't balance the equation, it's going to be very difficult to find the mole of H2. So we have 1 here, 1 Na, 1 Na, 1 O, 1 O, 1 and 2, 3 H's. Again, we want to make sure we have even numbers. So we're going to use whole numbers to balance in front of the compound or the elements. So since I have 3 here, I want to get an even number. So I'm going to put 2 here to get 4. And then put 2 here, 2 times 2, give me 4 hydrogen. So we're okay with that. Since I have 2 sodium here, I have 1, I must put 2 there. Now I have 2 sodium, 2 water, 2 sodium hydroxide to 1 H2. Now the first move after balancing the equation is to convert the mass of sodium into moles of sodium. And so we're going to say moles equal mass over molar mass. And we know that the mass is 9.2 grams over the molar mass of 23 grams per mole. Again, 9.2 divided by 23 is equal to 0.4 moles. So now we know the moles of sodium. How can we find the moles of hydrogen? We're going to use the mole ratio, which we must state. Remember, so now we say Na to H2 is 2 to 1. Now this is ratio. A ratio of 2 to 1 is saying that 2 to 1 is the same thing as 2 over 1. So whatever the moles of sodium is, the mole of H2 is half that value. So the moles of sodium here is 0.4, so the moles of H2 must be 0.2 since the mole ratio is 2 to 1. So we can write mole of H2 is equal to 0.2 moles. Now I know the moles of H2. I can now find the volume, which was what we were asked in the question. So to find the volume now of H2, we must use the formula moles equal volume over 24 at RTP. So we'd say now mole equal volume over 24. Therefore, volume equal moles times 24. And this will be equal to, the moles here is 0.2 moles times 24 dm³ per mole. So again, mole would cancel mole. So 0.2 times 24 would give us 0.2 times 24. And that would give us a value of 4.8. So 4.8 dm³. So this is saying then that a volume of 4.8 dm cube of H2 was produced when 9.2 grams of sodium reacted with water to produce these sodium hydroxide and H2. So we see that the principle is the same. First, write your equation, balance it. Secondly, use the quantity given in the question to convert that quantity to moles. Then use the mole ratio to find the mole of the required substance. And finally, convert the mole of that substance into what is required, whether it be mass or volume. Now, sometimes the mole ratio is not as straightforward as 1:1 or 1:2 or 2:1. So let's use some figures here. Let's start with a letter A to B. If the mole ratio is 1:1, then the moles of A is the same as the moles of B. Let's go to A, B, 1:2. If we know the moles of A, then the moles of B is twice the moles of A. Again, let's go to A to B. And this time, let's go 2:1. If we know the moles of A, then the moles of B is half that value. But suppose we have different values now. So A to B, and let's say the mole ratio is 2:3. Not as straightforward as saying, well, they are the same if it is 1:1, or if I know one, then I just multiply the other one by 2, or divide them by 2. 2:3 is a bit more complicated. So let us say we know the moles of A to be equal to, say, 0.5. What is the moles of B? Now remember again, it's not straightforward. But we know that 2:3 is the same thing as 2/3, which is ratio. And if we know the moles of A, we can write the moles of A for that ratio of 2. And we want to find the moles that correspond to 3. So all we need to do now is cross multiply. So we'll say 2x equal 3 times 0.5. Therefore, x equal to 3 times 0.5 divided by 2. So 3 times 0.5 is really 1.5 divided by 2, which is equal to 0.75 moles. So if the mole of A is 0.5, according to the mole ratio of 2:3, the moles of B is 0.75. And that is how you would calculate mole ratios when they are not as straightforward as 1:1 or 1:2 or even 2:1. This concludes another lesson in our chemistry lecture series.